The recording doesn't
all right. Okay. I've chosen, and they're necessarily of a rather elementary nature to fit into the time for this talk. I thought I'd give a very quick history of the subject, because the interesting point about the history, I think, is that, and I'll focus on two groups of people, well, Van den Dries on the one hand, and Anne Pillay and Charles Steinhorn on the other. Van den Dries approached the subject very directly. He was interested in structures on the real, structures expanding the ordered field structure of the reals in order to discuss definability of expansions of such structures. And he approached it fairly directly, just focusing on the real numbers, whereas Steinhorn and Pillay were much more abstract, pure model theorists who sought to simply generalize the notion of so-called stability theory to see how it could apply to ordered structures, which are never stable. But interestingly, it's the Pillay and Steinhorn approach that, as it happened, gave rise to the applications rather than the direct approach on the real line. So let me start with the way back in model theory to discuss the notion of strong minimality, which is, so I'm really now talking about how Pillay and Steinhorn approached the subject of o-minimality. Now, I suppose modern pure model theory began with Morley's categoricity theorem. If a countable complete theory is categorical in some uncountable power, that means all models in that power of the theory are isomorphic, then in fact it is categorical in all uncountable powers. And so we call such theories uncountably categorical. Then there was an issue of what the countable models of such a theory look like, and it was conjectured that either there's exactly one or there's exactly Aleph 0. Morley didn't settle that question, but it was Baldwin and Lachlan eventually proved that conjecture, and it's their proof I want to very briefly discuss. I guess the conjecture is motivated by the three standard examples of categorical theories. One has the very trivial theory of just theory in all powers. One then has the next most trivial thing, which is the theory of a trivial set, of an infinite set with infinitely many constants distinguished. This is clearly categorical in any uncountable power, just by directly constructing the isomorphism, but it has precisely Aleph 0 models in cardinality Aleph 0. We have the infinitely many constants, and then there can be one more element, two more elements, three more elements, up to Aleph 0 more elements. The next most complicated theory after that is the theory of vector spaces over a field where obviously a vector space, the isomorphism type of a model is just determined by its linear dimension. In uncountable powers, this has to be exactly the same as the cardinality of the model. This is over a countable field. In cardinality Aleph 0, if the field is infinite, the structure can have dimension 1, 2, 3, 4, and so on, up to Aleph 0. Or if it's over a finite field, then since it has to be infinite, it necessarily has to be of infinite dimension. So we get one model in cardinality Aleph 0. And then finally, the most complicated example known, I think, at the time of a categorical theory, uncountably categorical theory, is that of a models of a given cardinality are isomorphic, but there are precisely Aleph 0 models of power Aleph 0 because they are determined up to isomorphism by their transcendence degree. The maximal number of algebraically independent elements, which again could be 1, 2, 3, 4, up to Aleph 0 in the countable case. Now what these theories have in common is that they have a dimension theory which determines the isomorphism type of the model. And so Baldwin and Lachlan abstractly defined a dimension theory in an arbitrary structure. So if we have an arbitrary structure, so we have a domain, infinite, always infinite, with some relations and functions, Baldwin and Lachlan took the most naive definition of the dimension theory, or before we have a dimension theory, we want to have a notion of algebraic closure, which is just linear closure in the case of vector spaces, which gives rise to the dimension theory, or literally algebraic closure in the case of field theory, which gives the dimension theory. Here, so we just define if B is a subset of M and A is an element of M, then we say A is in the algebraic closure of B if and only if there is a formula phi x bar y, this a bunch of parameters, this a single variable, a sequence of variables, and a natural number n such that M satisfies, there exists at most n y's such that phi b bar y, so if there are and a tuple of elements b from b such that M satisfies the at most ny. So this is only satisfied by finitely many elements, of which one of them is A. Okay, so that's the obvious definition of something being in the algebraic closure of a set. If there's a set which is finite with parameters in B, and A is one of them. Unfortunately, this doesn't have any good properties at all that you, in general, but what Baldwin and Lachlan noticed is it does if you make a minimality assumption on M. So assume assume M is strongly minimal. Sorry, I'll just say, yes, strongly minimal. Which means, i.e., every definable and we allow constants from the model subset of M is either finite or cofinite. Of course, since we're allowing parameters, then every finite subset of M is definable and every cofinite subset is, and so the word minimal is used, meaning there's nothing else that's actually definable as a subset of M. Of course, there'd be many things that are definable if you take pairs or triples, but now this isn't quite the whole definition. The definition has to be a property of the theory rather than any particular structure. So one has to say, and every n which satisfies all the same first order sentences as M has this property too. For example, the ordered structure of the natural numbers has this property, but not everything elementarily equivalent to it does. And then if we make this assumption, then strong minimality implies the operation here of algebraic closure has good properties. And a good theory of bases as maximal independent sets and dimension. So if we assume the structure is strongly minimal, then one can prove, for example, that there is a good notion of dimension of a structure, which in the case of vector spaces corresponds to linear dimension, in the case of algebraically closed fields corresponds to transcendence degree, and the dimension of a structure determines it up to isomorphism. Now, unfortunately, all strongly minimal theories are uncountably categorical. However, not every uncountable categorical theory is strongly minimal, but essentially what Morley had shown was that every uncountably categorical theory has a property called omega stability, which I won't go into at all, which implies the existence of a strongly minimal set, a definable strongly minimal set, and one can show that the dimension of that set determines the isomorphism type of the whole structure. And so by this method, Baldwin and Lachlan were able to just carry out the same proof as for vector spaces to show there must either be one or Aleph zero models of an uncountably categorical theory in size Aleph zero. Now, so that the minimality notion was already in place soon after Morley's results of going down to making an assumption about a domain of a structure concerning the sparsity of the definable sets and getting good results even when the structure doesn't completely satisfy that condition. However, this was not the approach taken by Van den Dries, so now let's go to Van den Dries he didn't use the word minimality or even the notion really, theories. I think he used the words of finite type, which is rather overworked, but we won't be using it much after this quick précis of Van den Dries's work. And he just considered expansions of the structure I usually call R bar, which is just the real numbers with its ordering, addition and multiplication. So the ordered field of real numbers. So in other words, he was looking at structures that have this structure but possibly other things, and he was trying to prove something about the definable sets when we add the exponential function here, which was an old problem of Tarski. And he defined R tilde as finite type if every definable subset of R in the language, in this language of, in this structure R tilde, whatever it is, is a finite union of intervals and points. Now we have to add something here, but can you see the analogy with the strong minimality? It's never the case that if a structure has an ordering, then it's never the case it's strongly minimal. In fact, for those that know what stability is, it's never the case that it's even stable in the sense of Shallal. It has very bad model theoretic properties according to the way pure model theory was studied up to this point, the kind of late 70s, I suppose now, early 80s. But the analog of strong minimality, if you do have an ordering, you see, strong minimality states that every subset of M that's definable is already definable just with the equality symbol. It's either finite or cofinite. So you only need equality. Here it's saying, well, we have an ordering, and we just recognize that ordering, but for subsets of R, the only definable sets should be those that are definable just with the ordering. So, so you could say this is I definable in just this structure. Okay, so, and then he hoped to prove results about definable subsets of R squared and R cubed and so on. But unfortunately, this definition isn't enough, just as it wasn't here. This, it turns out, if you want to use the compactness theorem of logic effectively, you have to say that you have to make this a property of the theory of the structure rather than a particular structure. So, and this is also the case, you have to put in the definition. For every M elementarily equivalent to R bar. So you have to, sorry, R tilde. So R tilde is, you start with some expansion of the reals, and you say, you call something of finite type if every definable subset of R is already definable just using the ordering, and that's true for anything elementarily equivalent to R tilde, every model of its theory. And then Van den Dries proves various structure theorems for definable sets back in here under this assumption. However, now let's talk about Pillay and Steinhorn, who were working much more in the traditions of ordinary pure model theory, and obtained, just really from using their viewpoint, rather than focusing on the real numbers, where you can use extra properties of definable sets, like if they're bounded they have a supremum and things like this, which won't necessarily be true in so they work much more, they kept much more kept much closer to first order definability and didn't import any extra properties you get from the reals. So Pillay-Steinhorn so you might say kept things first order by banishing all completeness, well, at least psychologically, all notions of completeness we have about the reals, and they just take any structure with an ordering and possibly extra structure. Yeah, it's difficult now to see how big a step this was, but it really was the case that up to here you couldn't do any model theory of anything with an ordering. It just violated all of Shallah's theorems. It was always the bad case in all classification theory of structures because of this property of lack of stability. So this really was quite a step. Well, at first they considered this to be an arbitrary ordering, but it soon became clear that the most interesting case is where it's a dense ordering. So where this is a dense linear order on M without endpoints, without a first or last element. They do the general case, but nothing much exciting happens if it's not dense. And then they say, well, then they call M, just M, is o-minimal. So they first introduced the term, and the O just stands for order. So it's just it's going to be a complete analogy with strong minimality, except respecting the presence of an ordering. So M is o-minimal. Well, we have the definition really. If every definable with parameters, and this is the tricky point, this is why it's not immediately a property of the theory, just a property of one structure, subset, so in the language of M is already definable in just the structure with the ordering. So that's why it's called order minimal. In other words, it's a finite union of singletons and open intervals, possibly half-infinite intervals. And then, by studying this very carefully, and with the use of the compactness theorem and very first order methods that they were brought up with from stability theory, they established the remarkable result. Namely, and this is the result I want to give some applications of. It's the most applicable result, and far more so actually than some of the results of Van den Dries, where he really was working to have applications in mind. It turns out that even for the reals themselves, it's this approach that gives you the application. So here's the remarkable theorem, structure theorem they proved. They actually showed that this definition on its own is first order invariant. In other words, we've only made the definition for one structure here. It turns out that anything elementarily equivalent to M also satisfies this. And that's non-obvious because of the use of parameters. So here's the big theorem that I want to give some, and so this is what I refer to as the method of o-minimality. So M is o-minimal, okay? In this definition, then there's a certain uniformity that you automatically get. Well, we just say then every n elementarily equivalent to M is o-minimal. Now, for practical purposes, what that means is, hence, or this is how you prove it, if phi x bar y is a form. Just say the language of M, so no parameters in phi. Then there is a natural number n which only depends on phi, the formula phi, such that for all tuples of parameters taken from the domain of M, well, or n for any model elementarily equivalent, then if I can use this notation, phi a bar M, meaning the set of x satisfying phi a bar x in M, is a union of, so we know it's definable just with the ordering, so it's a finite union of intervals and points, but it's actually the union of at most n of them, less than or equal to n intervals. Open intervals, say, and singletons. Okay, so it's so you get this uniformity for free, which you certainly didn't in the even in the strong minimality case. And so they went on to prove more, namely further. So they prove things where we're not just dealing with subsets of M. If psi x bar y tilde, say, for a possibly different length of tuple of variables, is a formula of the language of M, n equals n psi, such that for all a bar taken from M, the set of let's say these are n tuples. So this just means the set of n tuples where n is the length of the variables y tilde. The set of all n tuples in M satisfying psi a bar y tilde is the union of less than or equal to n psi what are called cells. And now a cell is a particularly nice kind of definable set, which I don't want to go into the precise definition, but let's see how we do. Where a cell of cells, I'll just say here, of dimension d, for various d, equals 0 up to n. For d equals 0, a cell is just a point. A zero cell is just a point. For d equals 1, it's a sort of interval. So a cell, a d-dimensional cell, is a definable set, actually homeomorphic to 0, 1 to the d, just the d Cartesian product of 0, 1, homeomorphic for the ordered topology. And this is whether or not it's a standard model. Strictly speaking, that's not true in full generality. That requires us to have a field structure on the original model. Okay, so let's look at some simple applications. So these are simple, but I think that's necessary for a general audience. Let me just mention, I wonder how many people have heard of Descartes' rule of signs. So I'm going on to the method, use of the method, in particular the use of this theorem. Suppose we have a polynomial, p of x, with real coefficients, which I'm going to write I equals 1 to k, ai, xi to the nk. Ni, sorry. Now that's a polynomial of degree nk, n sub k. So over the complex numbers, it has n sub k roots, counting multiplicities. As it happens, over the real numbers, it has an upper bound on the number of roots that only depends on k. That's Descartes' rule of signs. So this has less than or equal to, I think it's 2k minus 1 zeros in R. So the number of roots only depends on the number of summands, not on the degree. That's the rule. And that's quite easy to prove using mean value theorem or Rolle's theorem. So you might like to try and prove that. So that's an old theorem, but certainly Descartes doesn't approach the problem of more variables. So suppose we consider a two-variable polynomial. Well, let's say degree k in both with k's squared summands. And let's ask a similar question. Well, now, of course, that can have infinitely many roots, but we expect the zero set of this to be a collection of curves in R squared. And it turns out that there is a bound independent of degree, depending only on k, for the number of one cells. In other words, they're just pieces of just curves in R squared that the zero set here breaks down into. Now, how do we prove that? Well, we make a substitution. So theorem, the zero set of Q, so that just means the set of zeros as a subset of R squared, is the union of less than or equal to a number n that depends only on k, and not on the coefficients and not on the exponents, connected curves. They'll be connected algebraic curves. And what's o-minimality got to do with that? Well, you can see that it's almost a direct application of the Pillay-Steinhorn theorem, namely the uniformity of the number of cells that make up the definable set, except that we need the ni and the nj to be variables. rather than sort of a fixed part of Q. The Aij are also variables, but that's clear, that's true in the field structure. But in the field structure, the exponents cannot be considered as variables. That has to be considered as a different term in the language of rings, for each set Ni and Nj. Sorry, those should be. Okay, now it turns out this theorem is true, this one here, even if those Ni's and Mj's are allowed to be real rather than just natural numbers. And what we do is we simply make a substitution of, if we write x equal e to the t and y equals e to the u, then we get that q e to the t e to the u is equal to sigma ij equals 1 to k aij e to the t u I wait a minute, t ni plus u mj, right? So this can be considered as a term in the variables aij, t, u, and ni's and the mj's, not in the ordinary ring language, but in the language of the structure where we have exponentiation. So we have the field operations. If we allow ourselves the exponential function in the language, then this just becomes a term where we're now thinking of the ni and mj as real variables. Okay. And of course we haven't really affected the topology of the zero set. Well, actually we're only considering now the zeros where both coordinates are positive. But we can consider all four cases separately by substituting y for minus y or something like that. Now it turns out, I proved some time ago, that this is o-minimal. Actually, it's also model complete. So it was proved sometime in the 90s that this is an o-minimal structure, therefore theorem follows from the Pillay-Steinhorn theorem. See, because this is a term, so we have the new variables t and u, and the parameters aij, ni, and the mj's, and that theorem told us that there's an upper bound to the number of, well, in this case we look at the set defined by this equals 0. There's an upper bound that only depends on essentially the k, just the form of this term, rather than any particular values of the parameters. So there's one simple application. And of course this works in any number of variables, not just x and y, but x, y, z, and any fixed number of other variables. we get that the 0 set of the corresponding polynomial is the union of a finite number of connected sets where the number is independent of the actual exponents and the coefficients. It only depends on what's called the additive complexity of the polynomial. And this gave rise to a theory of additive complexity of certain functions, which is a very real rather than complex way of studying polynomials. Let me just give you one quick last application, and I'll start again with something apparently elementary, like Descartes' rule of signs, but this is a bit different. This is number theoretic. Oh, that proof, by the way, is due to Riesler. The observation that if you make the substitution of e to the x for x in a polynomial, this gives you a term in the language with exponentiation, and you can treat then the exponents as variables. Okay, section 4, I think. So I'm going to talk about a Putnam Prize problem. Again, I've chosen these because they fit nicely into the time and don't require too much prior technical knowledge. So I think it was in the early 1980s when it's very clever American university and school students do this Putnam Prize exam, usually with considerable success, but there was one problem in this particular year that none of the students solved, namely it's this. Well, all right, it is a theorem. Suppose alpha is a positive real number and n to the power alpha is a natural number for all natural numbers n. So I take the natural numbers positive. Okay. Well, how can that happen? Well, it happens if alpha is 2 or 3 or 4, and the theorem is that that's the only way it can happen. Then alpha is in there. Okay, that was the prize problem, which none of the students solved, so I issue it as a challenge. The proof's only 5 or 6 lines, but if you don't see how to do it, it's well, it's like all things. It's rather awkward. Anyway, perhaps I should mention that it's actually a theorem of also true, and this is due to Siegel, so this is a bit deeper. If you only need 3 bits of information, actually, if 2 to the alpha, 3 to the alpha, and 5 to the alpha are actually natural numbers, that already implies alpha is a natural number. But it's unknown if you just have 2 bits of information. If you just have 2 to the alpha and 3 to the alpha are natural numbers, does this force alpha to be a natural number? That's unsolved. That's called the 4 exponentials conjecture, essentially. It follows from something called Shanel's conjecture, which you'll no doubt hear about in some of the following lectures today in here. But this much is known, but not if you have 2 bits of information. Of course, you can't have just 1 bit of information, because you could take alpha to be log 3 to base 2, for example. Anyway, so we can solve this by remarking that the function f of x equals x to the alpha is certainly definable in this structure r bar x. Right? It's definable with a parameter for alpha. because it's e to the alpha log x. If you can define e to the x, you can define log x, so you can define alpha log x with a parameter, and so this is just e to the. And so I wondered if a bit more was true here, and it turns out, now one property that follows actually from the Pillay-Steinhorn theorem, perhaps not so obviously, well, it more follows from the proof, is that if a function from reals to reals is definable in an o-minimal structure, then it's differentiable everywhere apart from finitely many points. And even twice differentiable and 3 times differentiable, although the number of bad points goes up, but they're still finite. And from this, you can get a theory of asymptotic values of functions that are bounded. And in particular, it's quite easy to show that if if a function is bounded by a polynomial, then you look at the function fx, or you look at its derivative, then it's bounded by a polynomial of 1 less degree. And so you can do a lot of calculus under the wonderful assumption that every function you ever arrive at is differentiable as many times as you want. So that's another method of o-minimality, is that you can make as nice assumptions as you wish when doing analysis in o-minimal structures, and then combining that with a little known transcendental number theory, you can prove the following theorem. Let f from reals to reals be definable in some o-minimal expansion of the real field, and assume it's bounded by a polynomial. Assume that mod f of x is less than or equal to x to the k for some fixed k, and all x, or well, all x greater than 0, say, are all sufficiently large x. Then the theorem states that f really can't take many natural number values for natural number arguments unless itself it is a polynomial with integer coefficients. So let's just say assume fx is not a polynomial with rational, we have to say. So assume fx is not a polynomial with rational coefficients, when what I'm about to say is obviously false. Then for all epsilon greater than 0, and for all sufficiently large h, the cardinality of the set of natural numbers such that n is less than or equal to h and f of n is also a natural number. So, motivated by this problem here, is less than h to the epsilon. So, assuming f is not of a form where this is obviously false, so this could take natural number values for all natural numbers if it had integer coefficients, then in this sense, if it's definable, if we make the extra assumption that it's definable, then in fact the number of natural numbers between 1 and h, such that f of n is also a natural number, is rather small. say less than h to the half, less than h to the third. So in particular, since x to the alpha is definable, and one has to show that this could never happen if alpha is a rational number that's not a natural number. That's very easy. It's very easy to show from this hypothesis that alpha has to be irrational if it's not a natural number. So then f of x, x to the power alpha is, well, I didn't have to say that, I suppose. F of x, then x to the alpha is certainly not a polynomial with rational coefficients. So we get immediately from this, by taking epsilon equal to a half, say that n to the alpha cannot be a natural number for very large n unless alpha is. And the most recent work, which I don't have quite time to say, but I'll just mention it without writing anything, is that this is true even for functions of many variables here. Providing it's not, there we have to be a bit careful about whether it's, we have to generalize the notion of a polynomial a little bit, but morally this is still true even if f has many variables, and that brings us right up to date, I think, with o-minimal research. So I'll stop there. Thank you very much.
Are there questions, remarks? No? We thank Alex again. Is on the main
announcement. So we're going to move to the Puteano, which is just 4 minutes walk. And, this room will be locked, so if you